hi, so welcome back. We are going to finish up chapter 21. So one of the things to be aware of when trying to gather a phylogeny is that not all similarities actually indicate homology, actually indicate an evolutionary relationship. So something called convergent evolution is the independent evolution of similar features in different lineages to deal with the same environmental conditions. So independent So for example, we have the North American flying squirrel and the Australian sugar glider. One is a placental mammal, one is a marsupial mammal. They're not that closely related, and the similarities that they have morphologically, these wide flaps of skin that allow them to glide tree to tree, that was not possessed by the common ancestor of the sugar glider and the flying squirrel. So in other words, that is not a homology of those two organisms. That just arise due to convergent evolution because of a similar selective pressure, that this was advantageous in their particular habitat. So we say that such a structure, rather than being homologous, is analogous. So analogous structures arise from convergent evolution. And we sometimes refer to these as homoplasies, which I know is confusing because it sounds like homology, but a homoplasie is actually an analogous structure that arose from independent evolution. Another example is this marsupial mole versus the placental mole. They both have adaptations for a similar burrowing, digging underground lifestyle, but these traits arose independently from convergent evolution, so therefore they are not homologous, they are analogous, and we would call them homoplasies. So another kind of example of analogous versus homologous structures. So this is an interesting example here of a bat wing and a bird wing. So we can see here both examples of homology and analogy. So the actual the bones of the forelimb here are actually homologous, right? Their vertebrate ancestor had these, and so these are homologies. These are homologous traits. However, the wing itself is an analogous structure. The common ancestor of bats and birds did not have wings. Rather, these wings are analogous structures, aka homoplasies, that arose by convergent evolution, because they were both in ecological situations where flight was adaptive. Another situation that can kind of make putting together a tree and identifying a clade a little bit tricky is an evolutionary reversal. So an evolutionary reversal is another process that can give us traits that look similar but aren't actually homologous. So this is when an organism that possessed an apomorphic trait, so we'll say a taxon that possessed an apomorphic remember, that's the derived trait, reverts back to the plesiomorphic. more ancestral trait. So a great example is snakes. So the legless condition in snakes is actually resulting from the loss of a derived feature from a more ancient ancestor. So the ancestor of snakes had legs. They evolved this trait of legs. And then in the lineage leading to the snakes, this trait reverted back to a more even more ancestral state of not having legs. So it's what we call an evolutionary reversal. This also happened in a lineage known as the legless lizard. So the similarity here between these two are results of independent evolutionary reversals rather than homology. So that can be a confusing thing too. Sometimes when we have these evolutionary reversals, or just sometimes in the course of evolution, we sometimes have what we call vestigial traits. So a vestigial trait is a structure that has no apparent function in the organism that it exists in, yet it is homologous to a functional organ in another species. Or another, we'll say, a functional structure. And a great example is that some species of snakes still retain vestigial femurs of what once was a leg. So snakes have vestigial femurs, which is one of your major leg bones. Also, we see vestigial pelvic bones in some species of whales because in their common ancestor, their common ancestor of whales actually was terrestrial and walking and had bones like a pelvis. So sometimes because of lack of information, because of being tricked by convergent evolution or an evolutionary reversal throughout history, we have put together phylogenetic trees where our clades were not exactly correct. So there's a couple different ways that clades can go wrong. Now, obviously, a monophyletic clade is the goal. So that's this blue box right here, where we have a common ancestor and all of its descendants. And one way you can think about a monophyletic clade is that you could remove it from the tree, the whole clade, from the tree with one sort of imaginary cut. So some things that sometimes go wrong, we can have what's called a paraphyletic group. So a paraphyletic group is a group that includes the common ancestor and some, but not all, of its descendants. So we're missing somebody in a paraphyletic group. We also can have what's called a polyphyletic group. Now, in a polyphyletic group, we have multiple more distantly related taxa that aren't sharing the same common ancestor. We think they go together, but they don't. So E, F, and G would be, if we tried to group these together, that would be polyphyletic. So let's give you some examples. So if we group together, which we oftentimes do, reptiles, what we would call class Reptilia, that's a paraphyletic group. Because we have the common ancestor, but historically we have not included birds, which should be part of this clade. So we're missing somebody. So when we talk about the reptiles and we mean this group right here, turtles, lizards, crocodiles, non-avian, that's a paraphyletic group. An example of a polyphyletic group would be if we grouped together endothermic animals and called them a clade. Well, we would be wrong. That would be polyphyletic. Because they're actually fairly distantly related, and we wouldn't be including the common ancestor. endothermy arose independently in avian and mammal lineages. So that would be something that, where we could get tricked by convergent evolution. All right, so let's talk about actually constructing a phylogeny, and we're going to do this in lab, and I'm going to go into more depth in this in lab, so don't be upset if at the end of this PowerPoint you're not 100% sure how to put one of these together. There should be an example, a practice example in your learning curve, and also we're going to be doing this in lab. So when we want to reconstruct a phylogeny, we use characters, right? We use, structural characters, or we could be using molecular data to determine relatedness among organisms. And we often depict this in a character state matrix, which is what you're looking at here, right? So we have our taxa listed on one side, and we have several different characters listed, usually across the top. And then here the minus is saying, presence versus absence, or rather, let me correct that. We're saying whether they have a plesiomorphic or apomorphic state of the trait. Typically with the minuses being the plesiomorphic ancestral state of the trait, and the pluses being the apomorphic derived state of the trait. Okay? And I'll explain that as we go along. So the first thing we do when we want to put together one of these phylogenies is we determine the outgroup. Okay, so the outgroup is a lineage known to diverge before the lineage we are interested in studying. And we use this outgroup as a basis of comparison for our in-group, which is the group we are studying. So in this case, our in-group, which we're showing by this, parentheses here, are what we call the gnathostomes. These are animals that have jaws. And our outgroup is this organism called the lamprey, or group of organisms called the lampreys. This is our designated outgroup. We know that it is descended from the same common ancestor, but everything in the in-group is more closely related to each other than any one is to the outgroup. And again, we define the outgroup as a basis of comparison. And typically what's going to happen here is we determine the ancestral character state, the plesiomorphic character state for the outgroup, and in this case it's going to be lack of jaws, right? Lampreys don't have jaws. So we say our common ancestor and our early diverging lamprey group don't have jaws. The lampreys retained that plesiomorphic character of not having jaws. And then the in-group is having the apomorphic state of that character. It has derived jaws. In fact, we can say jaws are a synapomorphy of our in-group. And this character unites all these organisms together as a clade. And you can see we've kind of, so the minus is showing our plesiomorphic, and then, hey, look, everybody's got the apomorphic state in this clade. Then we're going to go through all these different characters, looking at all our different taxa in our in-group, and parse it out based on synapomorphies, shared derived characters. Basically, we tally up the shared derived characters, and the logic here is that groups sharing the greatest number of derived features are hypothesized to be the most closely related, and so we group them together. And we are going to get practice doing this in lab. We're going to be working with some of these character state matrices. So the final thing I want to talk about is, how do we know we made the right tree? Right, there's a number of different ways you can put things together. How do we know we did it right? Well, sometimes we don't. Sometimes we find out later we did it wrong. But the way that we go about determining, we have to make a decision about what tree we're going to go with. And the way we do this is using the principle of parsimony. Which says that the preferred tree, is the simplest tree. In other words, the one that requires the fewest evolutionary changes. Basically based on Occam's razor, this idea that the simplest explanation is usually the correct one. So if we're comparing two trees, the one that requires the fewest evolutionary changes is most likely to be the one that best reflects the actual phylogeny of the group. So looking at this example, this tree, tree A, is more parsimonious, right? The way we've grouped this, a backbone arises, and then we have hair arising once, uniting humans and dogs in a clade. If we look here and we separate out our clades differently, if we try to put lizards and humans together and dogs off separately, well, then we have to have hair arising twice, once in dogs and once in humans. And we know sometimes this does happen, but it's a less parsimonious explanation. So we'll also practice with this in lab. All right, so that's the end of chapter 21. It's been a blast. And I know some of this terminology can be a little tricky, so if you have questions, please let me know, and we will definitely be spending some time with this in lab. So hopefully we can clear any of that up.